del Supercomputer Center, lavora lì dal 2004. Io ho avuto modo di collaborare con lui perché siamo insieme, cioè lui lavora per un progetto della National Science Foundation americana che riguarda, diciamo, applicazioni della GPU in altre energie, fisica delle altre energie, e quindi è candidato attraverso un lavoro di esperimento esterno a CMS, è candidato con altri colleghi di un altro esperimento di fare rete, una piccola rete diciamo che tratta di fare esperimenti di appartenenze, e quindi questo è stato sostanzialmente la circostanza di cui è uno dei grandi esperti forse al mondo, e lavora essenzialmente nel campo della visualizzazione, soprattutto per applicazioni mediche.
Hello everyone, my name is Hittle, and I'm here today to talk to you about GPU applications for scientific computation. Just as an agenda, I'm going to give an introduction about where I work at, about scientific computing, a little bit about the GPU history. I will give some examples, and I wanted to share some of my insight about Doris, and then the direction that GPU computing is going. So I work at the Ohio Supercomputer Center, which is a part of the OTEC consortium. The Ohio Supercomputer Center provides HPC services to all academic researchers in the state of Ohio. We also have a company called Ornet, which provides a 100 gigabit connection to border Ohio. Any university gets access to this for free, and well, not quite free, but very cheap. And we've also been having initiatives for high schools, for grade schools, and sharing what we can like that. Ohio Link is a service that provides academic journals, papers, and other books, library books, all across universities. And then we have eStudent Services, which is a website that people can go to get tutoring. This is for anyone in the state of Ohio. If you're in high school, you have a calculus problem, you can go online and get help from someone within that specific domain. I work at the Interface Lab, and what we do is we take problems and we try to put a spin on it and set it out. So what we like to spin is, you don't want to just sit down at a computer and interact with something. You want to have your hands on the device, or you want to walk around the device and interact with the data. So what we like to do is we like to have interface devices, we have head-mount displays, we have tracking systems, and we try to put you into a virtual environment and let you interact with it. And just a few of our projects here. This one is called our, we had a PTO simulation. Does anyone know what a PTO is? It's called a power takeoff on the back of a tractor. This is basically the mechanism that powers anything that you have, any kind of instrument on the back of a tractor. And it's very dangerous. If you have anything that gets close to it, you're going to have a tragic accident with it. So they're very dangerous, and it's what we wanted to do is we wanted to see what kind of reactions people that knew what a PTO was, put them in the simulation and see if we get the same kind of response physically, not necessarily, they're not going to get a visual response. We're checking galvanic skin response to see if they're getting some sort of reaction to it. Another application we have is is for NIOSH, which is a home healthcare project. Home healthcare technicians go into someone else's home and to take care and maintain people. And what we are trying to do is have awareness for different hazards that someone might find within a home environment. Having a faceplate on an electrical outlet, if you're missing that, you can have a shock hazard. Dealing with how to interact with people in that sort of sense. And then the final project I'll talk about is our temporal bone simulator. Our PI is shown there with the system. They have haptic feedback devices, so it's an instrument that's like a pen with a bunch of motors and wires connected to it, and you can feel a 3D representation of the bone underneath. And he's wearing stereo glasses. The surgery is done under a microscope. So what is scientific computing? It's using computers to analyze and solve scientific problems. There's a number of applications for that. So there's numerical simulations. If you are into meteorology, you need to find what numbers you're going to plug in to predict the forecast. And they use clusters in order to do this computation, because depending on how the wind blows, something else could happen. At least that's in Ohio. Model and fitting, these are also used. So if you want to find the probability of something that's going to happen, and there's a wide variety of points, this is something you would use as well. And then we also have computational optimization. Machine learning is a big one. Using an algorithm to look at the problem and analyze it and figure out what's the best way to change it, to make it either respond quicker or find a better way to handle it. One really good example is taking a look at bottles of water. Plastic itself needs to contain the liquid. It also needs to support all the other bottles that are going to be found on the pallet. So finding the right contribution of plastic in order to keep the bottle from just compressing in on itself and squishing all the bottles, you need to take that into account for the entire pallet. So some scientific applications. This is coming from only one language, CUDA. There are over 275 different applications that are commercialized right now that are using GPU technology to increase the computation and visualization. A little bit about the languages. You will need to write a specific language and code in order to write software for a GPU. There are some plug-and-play type. You can use a library, and FFTW is a good example. CU FFTW basically has the same functions, the same signatures, except they have a CU at the front of it. So you don't have to have too much coding, duplicate coding just to use it. You can just go in and add a CU and you're ready to go. CUDA is closed source. So what I mean by that is that closed source in the sense that they are proprietary. They are more bleeding edge. So when you're using CUDA, you have a much higher chance of you buy a new card, you're using the latest and greatest technology in order to access those features. OpenCL is another one, and this one's really, really neat because it doesn't, CUDA is specific to NVIDIA products. OpenCL isn't, and OpenCL is targeted for any platform. So it's targeted for NVIDIA GPUs, AMD GPUs, I think Xeon Phi is also, yes. And then this is a collaboration for the spec, and it has its pros and cons. So the last language that I wanted to talk about is Silk, which Silk is for the Intel Xeon Phis, and those are, you're going to get the best results if you use an Intel processor along with the Intel Xeon Phi, since the compiler is going to be the same along with the accelerator as well. And I kind of alluded to this, but I wanted to mention a little bit about accelerator devices. When I say accelerator, I'm talking about GPUs. So we do have FPGAs, and FPGAs are extremely difficult to program for. They are used for very, very high-speed transmission. So if you're doing video streaming and you need to do something, a lot of FPGA work is there. Same with the networking. We also have the NVIDIA and AMD GPUs, and the entertainment industry is very big with this, along with a lot of scientific applications. And then the Xeon Phis, which are getting more and more mainstream. They're a little bit different than some of the GPUs, but they are a very low-end x86 processor. So they have their own niche right now. So what is GPU computing? GPU, which was coined by Mark Harris, which stands for Generic Processing Computational Graphical Processing Units. So what I have here is a picture of an 8-core Haswell processor, and just for the sake of comparison, I also added an NVIDIA M6000, and we have 8 cores versus 3,000. And I think everyone can see that if you can take advantage of 3,000 cores rather than 8, that sounds like a win. A little bit about the CPUs. So the CPUs are very good for controlling everything that's in the system. That's what they're designed for. So if you do anything with the network, if you do anything with any kind of peripheral, that's kind of their job. The cores execute independently, which means they have a lot of logic that involves they are able to stay independent of everything else that's happening in the system. They have a very fast clock, so the amount of time that they execute, so they just sit there and spin for a long period of time, and that is really important. They're much faster than a GPU core. They're able to execute instructions much faster than a GPU. They have great branch prediction. So if you're traveling down a road and you have a left turn and you have a fork and you can either go left or right, they're very good at saying, I already know which direction I'm going to go. I'm going to go both. And then when I actually figure out what I need to do, I already have everything in memory in order to continue on. They're very good at this. They are designed for general purpose programs. There's no scientific processor that you can buy that's going to be able to do this. And just a little bit about the memory latency. So the CPU cores are designed to get memory as quickly as possible. If you look at, so I have just this layer we have an L1 cache, an L2 cache, and an L3 cache. For the CPU core, it needs to have everything on the core. If you say, oh, I need a piece of information, and it's not on the core, then it has to go to the L1. And when it goes to the L1, it says, okay, do you have it? Yes, I do. It takes 10 clock cycles in order for it to get that piece of memory back up. If you say, I need a piece of memory, but it's not an L1 and it goes to L2, then you have a factor of 100. So all these clock cycles build up if you don't have that cache ready, that memory in the cache. And then it'll eventually go to the system memory. So on the GPU side, we have a lot of cores. We have a large factor more. They all execute the same instruction at the same time, which I think is very important. So when you have a parallel problem, it executes it all across the board. It's not just one core doing one job. They have special instructions, which CPUs do not. So they have one cycle instruction calculation for sine, cosine, square root. They do run at a lower clock speed, but what you gain and benefit is that they all run at the same time. And they expose data parallelism. So when you are doing memory accesses, the L2 cache is shared amongst everything. So all of these cores, some of the cores share an L1 cache. And here you can see this image. There's 8 cores. This is a G80. All these 8 cores share an L1 cache with another set of 8 cores. So if you have something, a thread that's running right next to another thread, and that's what will happen, then all of them get access to this L1 cache, and you take advantage of it through the parallelism. And the one big thing is that there is no branch prediction. It's going to be easier to recompute the calculation rather than have some sort of, where am I going on the road? Am I going left or am I going right? Well, you need to figure out a way that you can remove that if possible. It's not always possible, but. And the neat thing about this is that they are available on your laptop or your desktop. So if you have it, you have it right there, and you can take advantage of GPU computations. So a little bit about GPU history. the GPU has been driven by the video game industry. Last fiscal quarter of 2014, I took this from NVIDIA. They revenued $1.14 billion from only the GeForce market. This does not include Tesla or their Quadro line. It's $1.14 billion. It's huge. The first microprocessor that they had was in 1986. They had a processor and a coprocessor, and that coprocessor was dedicated to doing graphics. This has been around a long time, but it never really hit consumer markets for quite a while. You have dedicated hardware, so back in the day, arcade machines, consoles, all this stuff. And I added this in because we used to have one of these SGI Onyxes. This machine was $250,000. And going from $250,000 to $3,000 to $1,000, it's definitely more for, at least for us. And this machine was released in 1995, so it's only been 20 years. And for today's graphics, I know this is the text is a little hard to read, but this is for the graphics pipeline, and the boxes in orange are the important part that I wanted to mention. Those boxes are the programmable pipeline, and that's where graphics can come in and say, I want to make a modification in the pipeline, and you can write it. And this is what spawned GPU computing. This is what spawned GPU computing, because people recognize that they can make modifications, and these are just 2D textures, and they can put their problem as a two-dimensional image, put it on the GPU, perform the calculation, and then return a result. And that was really critical. And as you've already seen, this is the latest hardware today. This is the Quadro M6000. So there's 15 of these large blocks, and you can see that all of these little green boxes are the cores, the GPU cores. Over here they have the special instructions that will allow you to do the sine cosine for 1 clock cycle, and there's some load stores and lots of good information with that. So I already mentioned that they have 3072 cores. They have 12 gigabytes of memory. They're using a PCI Generation 3. Hyper-Q is pretty neat. You can have multiple processes that are accessing the same graphics card at the same time, and it'll execute the kernels at the same time. Before they would do it, but it wasn't at the same time. It was time shared, so it would start with the one kernel, then it would switch it out, and then execute the next one. Dynamic parallelism gives you the ability to have one kernel that will call another kernel underneath. And that, of course, can be very problematic. But some of the problems, though, is that they generate a lot of heat. Power is a huge issue. They use a lot of power. And the biggest limitation with internally is the PCI Express. And so finding some way to get around that is always a great option. So going into an example, I have a really simple example that's showing a matrix multiplication. So matrix multiplication, this is my output over here, A, B, C, D through P. And what I want to do to calculate A is I want to take the row right here, and then I want to take the column. So it should be 1 times 1 plus 2 times 1, and so on. And there we go. So I had an answer of 10. And then to do the same thing with a different point in time, so this K value is this third row multiplied by this third column. And I add those all up, and then I save it out. And then what I wanted to show was a real simple example that I wrote in C++. And what I'm doing here is, I'm looping over the output. So I need to go over where all of the points are in this A through P matrix. And I want to do a summation. this might be wrong. Yeah, it needs to take into account which column and row. So there'll be a column and a row, and then you'll know exactly where you're going to go. You're going to sum them all up into a total, and then you're going to write it. So for a CUDA example, you're going to do the same thing, except this is going to actually remove the first 2 for loops. And that's really what you need to recognize when you're writing parallel algorithms with CUDA, is recognizing how you can take apart the problem and then apply it as a kernel. So this kernel, thread ID X, thread ID Y, these are common nomenclature to identify which thread you're working on. You don't know which thread you're going to get, so you need to figure this out. And then you divide the problem based on that, and then it's still the same wrong algorithm. But you would need to figure out which row and which column you're going to be sampling from. You loop over them, you add them up, and then you write the output. And so that seemed pretty easy. So I gave a really simple example here to show of how the threads would be divided up. So you have a 0, 0, you have a 0, 1, and so on. And it doesn't matter which threads actually run, because they're all going to run at one point in time. You write your code, and as you write your code, it'll figure it out, and it'll decide how it's going to schedule it. You need to copy your data over. So in this example, this is a pretty poor example, because you're going to copy over 16 times 3 values, and they're really small. So you do need to have a large amount of work, and it's very important. These don't work on small problems. You have to have huge problems. You want to limit your copies as much as possible. If you can, you keep it on the GPU for as long as possible, and then you return with the value. You don't transfer, do a computation, bring it back, do a transfer, and you want to avoid that as much as possible. And then of course, profile. So my examples were very simple to try to be clear. They weren't optimized. And you want to use something like Insight, or Insight is for CUDA. It's provided by NVIDIA. Or you want to use CodaXL, which is provided by AMD. Those are the CUDA and OpenCL profilers. And what it'll do is it'll show you how the kernels run, what percentage the occupancy was. So occupancy is the term that's used for determining, am I filling up the work on the GPU, and is it continuously being busy, or is it not? So another example, this is a bit more complicated example. So we have an interactive simulator in which we're trying to train and assess surgeons on how to perform surgical surgeries. We have 12 institutes across the United States, which we have them collaborate. They came up with a set of metrics. And what we're doing is we're having each expert drill a bone. We're having residents drill a bone. We're going to have the experts grade the bone, and then we're going to have automated software that tries to match what the expert came up with. And hopefully, if everything works right, we won't have to have experts take 20 minutes to an hour to grade these sessions. We'll have a system that will say resident scored 100% or the resident scored 50, and if it's 50, we can identify those and get them more help. So what is a temporal bone? It's on the lateral side of your skull. So if you feel right behind your ear, that bump, that's called your mastoid. And you can see here on this image, the mastoid is right here. This is the ear canal, and then your jaw fits here, so this would be a left bone. It contains the organs of hearing and balance, and there's a lot of critical structures in here. If your facial nerve runs through there and it innervates the side of your face, so if something were to happen, it'd be a very tragic accident. They would lose all innervation of the side of their face. And it's used for controlling infections. This usually happens in young children or elderly. Cochlear implants, you can't hear that they drill away everything to stick in a cochlear implant. And then tumor excision. All of those are the beginning stages of this surgery, and it's very complex. So what we're doing is what's called volume rendering. The way I like to think about it is a loaf of bread. So you can take a piece of bread out and you can look at it. It's a two-dimensional image. You can kind of rotate it around. But when you put it back in, you have an entire loaf of bread that you can turn and rotate around and interact with. And that's what we're taking advantage of. We collected micro CT data sets. Our resolution is 98 microns. And we have specific requirements for our volume renderer. It has to be interactive, which means we have to have 30 frames per second rendering speed, and we also have to have stereo. The surgery is performed under a microscope, and we have to have that stereo. We get a lot of information from depth, so we require that. We could potentially use GLSL, but with CUDA, there's actually the potential for having much higher speed with it, so we chose the CUDA option. Depends on how you subdivide the problem. And just as an example, we have a camera, we have our display. So our camera for our system would be some imaginary point we have out front of the monitor, and then we have our image here, which is where we're drawing our image. And the way we're dividing our CUDA problem is basically taking all those pixels and making blocks. And with those blocks, we shoot rays from the camera into the scene to see if we intersect with the volume data set. And then we pass it all back. So here's an image I took of the actual surgery, and here's an image from our simulator. The one thing to note, and it might be a little difficult to see, is that in the surgical image, right over here is a slight tinge of blue. And the surgeons, there's no way in the world I can do their job. They see so many colors that I can't discern them. And we have to simulate that, so you can kind of see a blue tinge over here, and of course drill the incorrect spot, so there's a little red spot as well. For the data processing side, we have an image class that breaks the problem up into large chunks. So what we do, we have a lot of data processing that's used. So some of our calculations we have in a road, a single process, so one CPU on one machine takes 8 minutes to run over this data set. We have a CUDA-fied example, that runs in less than a second. So we have a huge speed up, and this is very important when you're talking about taking, eventually, you will take clinical data, process it, put it in the simulator in under 20 minutes. And that's a big turnaround time to do preoperative assessment. And I wanted to switch gears a little bit. So a little bit about INSAR, and it stands for Interferometric Synthetic Aperture Radar. This is a process that is used by geodesy, the scientific domain that's trying to understand what the Earth's shape is like, its orientation in space, and its gravitational field. And the cool part about this is it's all over time. And it's also used for remote sensing. So if you are trying to figure out what's happening in somewhere that you can't actually visit, so we would use this technology in order to observe it from afar. This is done through either ground, an airplane, or satellite. And this image was great to really help understand. So it has like a master-slave setup. And in this setup, what they're looking at is shooting radars from these two different points in time. They're shooting it to a surface, and then they're bringing back the phases, and then they're trying to figure out what is actually happening with that. And the neat part about it is that the radar goes through clouds, and you can do this at night, and the signal does depend on the slope, so it has its own set of issues, especially if you have roughness, and if you have sand as a good dielectric constant. That sand, things with static fields, and those cause issues because they are changing the phase. So as it bounces back, it's giving you different problems. So the Dora software, what it's doing is it has a suite of different applications that it's doing. And one of them is to calculate a coherence image, which is basically the relationship of these two different instances in time, and they're trying to figure out information from that. The interferometric portion of it is trying to figure out about what's actually happening with these physical waves as they come back, the differences between them. And you're mapping this to some sort of physical location. So sometimes it could be, typically it's a flat surface, or it could be, and then you're trying to map it onto a sphere. So this is kind of the relationship that's happening between them. And then filtering is always a huge image processing problem. So you want to make sure that the changes are happening gradually. And negative pi to pi, since it's a sine wave, you're going to have peaks, and you need to figure out the differences between them and make sure that they don't overlap. And what I did was, I'm a computer scientist, so I profiled it. And for profiling, a little bit about it. So what I'm interested in is what's the most expensive function, how many times is it called, and what is it doing really in the long run. And we're looking at memory consumption as well, but I didn't really look at memory consumption for this particular application. There's two different types of profilers. You have a flat profiler, which kind of gives you a really broad generic. This is the screen window as you're looking into it. And then they also have call graphs, which give you a much clearer description of what's actually happening as it breaks down. And then, of course, you want to, once you identify which functions are the most expensive, you want to go in and examine it, because maybe you're doing memory accesses in a little bit differently. Maybe you need to look and see if someone else has done a different algorithm. There's different approaches to this, and it's all about identifying where it is. And I just wanted to mention the tracing option, which is very good for if you're a C programmer and you put print statements everywhere. This is kind of the same thing where you would have a read time before a function, read time after a function, and print it out. And that's very helpful as well to help you identify at least locally which functions are being very expensive. So I took a look at this. There was 3 different configuration files that I ran. The first 2 had pretty much the exact same results. Oversample, so it was taking one of the images, and based on the theory that you have it's the Nyquist theory, you have some sort of signal, you can reconstruct it by oversampling it and making the time steps even smaller, and you can reproduce the whole signal from that. So that's what this oversample SLC function is doing, and it's occurring twice in this case. The MALDC3, which is a complex number multiplication, is also very expensive, but we might be at the limits of being able to deal with that in particular. So that's something that we would want to look at and not necessarily be able to do anything with. And then and the other results, the complex multiplication is there as well. We also have a complex matrix multiplication that's happening as well. So I'm sure that there's some either a transformation or some sort of change that's happening underneath. And so I want to identify where that's happening and see if there's anything that we can do around that. And some of the FFTW functions that I recognized, which was in 132, these are all complex fast forward domain transformations and then back again. So I want to identify what these are, what they're doing, and see what we can do about it. So one thing I would do is probably replace these with QFFTW and see what results I would get. So the future of GPU computation, this is, I'm going to start with the hardware. I see more cores, more memory, all this stuff is going to continuously grow. They've been developing 3-dimensional memory. So, and this is very interesting because they're reaching the limit on the 2-dimensional space. And what they need to do is stack the memory chips on top of each other. So not only will they have a 2-dimensional line for transfers to the hardware, they'll have a line that goes up as well in 3 dimensions. NVLink is interesting as well. This is NVIDIA's response to the PCI Express Plus is too slow. This is, I believe it's released in two supercomputers right now, or it's going to be released, and it's 3 times faster. It's 3 times faster than PCI Gen 3. So we have some opportunity to see what results come of this and see if it grows or if it diminishes. Better scheduling. The scheduling systems have needed improvement from the CUDA side as well, and they continue to make improvements for this. So different kernels can sometimes not figure out what needs to run, and then you have all these changes that need to happen in order to bring in one context of kernel and with another context of kernel. So they've been making the improvements there. And then of course, ARM processing. Everyone has phones, and you know the ARM processing, the ARM processors themselves are low power consumption, but they're also pretty fast. Open Power is a standard that has been created to help industrialize ARM processing, and Tegra's in this case as well, so that hopefully we can create supercomputers that still have the same amount of computational power, but with a lower footprint. We definitely have a very high, working at the Supercomputer Center, we definitely have a very high power bill. And on the software side of things, it's just as interesting as well. So if anyone is a C++ programmer, a lot of the standards that are being introduced into C++ 11, they're including them. So Auto, Lambda, they have a number of these features to help make writing your code easier. And they've also got a standard in to try and parallelize the STL library. So if this works, underneath, it'll use any accelerator that you have available on your machine to speed up your code, and you won't have to do any coding. You will already have everything set up, and it will take care of it. Some of the problems that they're addressing, so allocating and deallocating memory.